Should we start? Yay. Welcome back. Okay. So it's still me, it's still Maxim, it's still the same Twitter handle, right? So oh, good. Perfect. And this time I would like to talk about, we kind of defined the whole series as data-oriented design because there is this idea of data-oriented design where the main thing we think about data in the first place, right? So, and I think data representation and serialization is one part of it, important part, because it's basically the basics, right? How we actually store data in a way. And then the next topic will be about a software development pattern. I'm a little bit, I'm not a big, I don't like the word architecture when it's about programming. This is why I try to avoid it as far as possible, because I think that what we do with programming is not necessarily reflects with architecture and building buildings and so on and so forth. But different topic, right? This is why I basically say okay, this one is more entity component system is basically a software development pattern and how a different way how you can think about building software, specifically when it comes to interactive programs. And yeah, so let's start. So in order to compare it with something, I would like to first start with paradigms that we know, probably. Who knows object-oriented programming and uses it? All of us, right? So it's basically it's predominant one, it's the one which are currently as well taught in school and so on and so forth. And most of the people agree that if we have object-oriented programming, it's a good thing to follow the solid principles. Who knows the solid principles? Most of the people. Not by heart, but generally. I will actually go through the abbreviation at some point, so don't worry. Right, so the idea is here, normally when we talk about object-oriented programming, one of the examples which people love, and I don't know why, it's shapes. And it's rectangles and circles and computing of areas. So if you go and search for open-close principle, which is one of the solid principles, one of the first blog posts which you will find is this one, and it discusses the idea of open-close principle. And I found it actually, it's an okay example to go through and see how it's actually applies to entity component system and so on and so forth. But first start with this blog post. I just took the code that was in this blog post and to kind of familiarize with the problem and so on and so forth. Right, so idea is following. It's interesting that sometimes it works. Okay. Sorry, yeah. Okay, so we have a rectangle. This is C#. Who can read C#? It's, who can read Java? It's like Java, but a little bit different. So this stuff is not Java-like, but it's basically, I'm telling you that we have these properties, width and height, and then this will generate getters and setters for us, right? In a way. A little bit nicer than Java, in a way. Don't kill me. All right, so here we have a rectangle which has width and height. Simple, it's a class. And then we have another class. I will just tap it here. We have another class which is an area calculator. And this class have a method which is an area which receives an array of rectangles, and then it just calculates the area in a way and returns it. Simple, right? Representation, and then we have a computation in this other class. Cool. But the idea is we had rectangles. Now we introduce circles. And now if we keep it this way, we say like, okay, now this method receives not an array of rectangles, but an array of objects, something, right? And then we just say like, okay, we iterate through all the shapes, and then we check the type. If it's a rectangle, then we do the computation for, we cast it, and then do the computation for the rectangle area. And otherwise, we're certain it's a circle. A bit, yeah, but, you know, okay. But the idea of open-close is basically to say like a class should be open for extension and closed for modification. Meaning here, basically we say like we introduce circle and we say it's a circle. If we would like to introduce a triangle, we would have to modify this class, this method, which is not really smart, right? So we see the problem here, right? So it's kind of like it scales badly, you have to modify and so on and so forth. So what we can do, according to the blog post, is we can define an abstract class called shape, which has an abstract method area, which will return the double, so the area we have. I personally would rather go with an interface than an abstract class, but again, it's not my example. I'm just going with a blog post. It's kind of like potato in a way, you know. So yeah, this is the idea. And now what we can, now we say that a rectangle doesn't only have the data, but it also have the computation logic. It says it like it inherits from the abstract shape, and it has to override this method now. And here we have implementation of area, right? And with circle, we have it also subclass shapes. It only has a radius, and then the area is radius multiplied with radius multiplied with pi. Makes sense, right? Here it's a very nice object-oriented approach. We have data, we have cohesion, so the methods works on the own data and so on and so forth. Like, perfect. Object-oriented design. And now we can say in this area calculator, we say that now in the area we expect array of shapes, right? We iterate through the shapes, and now we actually ask shape for its area. And this is how we can come to the sum of areas. This one is actually scales quite well, right? Because if we introduce another class, we don't have to change this method. We just introduce something new, and then just rectangles and all kind of different ellipses and so on and so forth, right? Great. So, like, I think what it shows is basically that in object-oriented programming, the main thing is abstraction. We introduce the right abstraction, and then it kind of, everything starts to work. So we say, this is an abstract class, shape, and then things working. However, I feel like what we do with abstractions in object-oriented programming reminds me a little bit of abstract art. Right? It seems very simple. It's just lines, right? Lines, circles. But if we look at this and think about, like, what is it? It's a sun, maybe, because it's a circle and in the right place, and this could be a church or something, and then it's a city, maybe, it's something big. So we have lots of associations with those very simple things, right? Just lines. And it's interesting if you look at this, think like, okay, a kid could draw something like this, right? Technically, it's very easy. It's just like take a linear and do some circles, and this is it. But actually, you have to be a very skilled artist in order to make from this kind of simple shapes something as complex and appealing and interesting. And I believe that in object-oriented programming, it's kind of the same. The concepts are simple. You just say, like, okay, you say a rectangle is just two properties, which is already quite abstract, right? Like, rectangles is like It can have color and so on and so forth. And we only concentrate on the small things, and then we kind of like evolve it. And we normally, like, I believe it's very metaphorical. So all these classes actually is a metaphor for us to say, like, when I think about rectangle, I expect there to be width and height and maybe area, which is also not always true, right? So sometimes if I ask all of you what are the properties of rectangle, I guess different people will actually tell different properties because it's all about like associations and metaphorical thinking in a way. Okay, let's do functional programming. Who does functional programming? Lots of people here. Yeah, finally, I don't really, to be honest. Like, I do a little bit of it, but I'm not a pro. But what I kind of do is, like, this book, I read this, nice Haskell for a greater good, perfect. And the interesting part is I also, in this book, there is also an example how to compute area of a rectangle and a circle. Like, somehow people just love it. This is like the first example that I think about, so great. So if I go through the book, I saw this implementation. Who's familiar with syntax of Haskell? Most of the people, okay. So like, it's basically we define a function which have a float, and returns a float. It's a little bit, the notation is a little bit weird for people who don't come from Haskell background, but you have function carrying and so on and so forth, blah, blah, blah. So like, doesn't matter much. We say just basically we have this rectangle area and we receive A and B, and the result will be A multiplied by B. However, this goes well, but what about if we would like to have a more generic case? Right, and later in the book, there is a chapter about the types, and there is an introduction of a sum type, which you can define. And then we basically say, like, okay, we have shape, circle, with a float, and we have a rectangle with two floats. And it's a sum type. It's basically we say shape can be either a circle or a rectangle. When it's a circle, it's only encapsulates one float. If it's a rectangle, it encapsulates two floats, right? Then we define the area function where we say, like, okay, we take a shape and we return the float. And then we have different implementations for different shapes, in a way, right? We say for circle, it's P multiplied by R. For rectangle, it's width multiplied by height. All good, right? Makes sense. Then, if we would like to have a sum, however, this is how we write it in Haskell. A little bit cryptic, so basically what we say like we have a list of different shapes. It can be circle, rectangle, circle, and then we map the list over the area function, and then we apply it to the sum. So in functional programming, in a way, I believe it's more about function composition, right? So it's kind of like input, functional composition, and then you have the output, right? Kind of in this way. Okay. Now let's talk about entity component system. When I think about this problem in entity component system, the first thing I think about is something like this. Spreadsheet, in a way, right? So I just say, like, okay, I have something, context or world, where I say I have different entities, like entity 1, 2, 3, 4, and then entity 1 have a radius, entity 2 have width and height, entity 3 have width and height, and entity 4 have a radius. I don't even talk about rectangles and circles, because basically I don't care. I just concentrate on what is the data which I need to achieve my task, in a way, okay? So, and then you can see that I have this area and it's empty. Right? Right. So like this is kind of a pseudo implementation in C# again. So how do I achieve it? I just basically say like, I have this component, I have a radius component, I have height component, width component, and area component, and they have just float values. This is how I represent this stuff, right? And then an entity is kind of a product type. I can add, like I can combine the components, and depends on how I combine them, they become a rectangle, for example. If I combined height with width, it becomes a rectangle. It's not explicitly telling I'm a rectangle, but if somebody has width and height in my domain, I know it's a rectangle. If it has a radius, then it's a circle, without explicitly defining what it is, just based on the composition, right? Then how do I compute the circle of area? I have this compute circle area system. So we have this ECS, entity component system. This already kind of like MVC, model view control. It just basically defines what kind of building blocks we have there. Entity is the thing which aggregates components. So it's the thing, logical, which have different components. And then the system actually works with these components to do something. In the entity component system, what we do, we separate state from behavior. Contrary to object-oriented programming, where we say we would like to have cohesion and keep everything kind of close by and work on our own data in a way. Okay, so what we do here in compute circle area system, we say, please give me all the entities which have a radius component, and then I will compute the area itself based on the formula in a way, and I will set the area component on this entity. So basically this. So I'm going through the entities, and now if I see radius, I will compute the area, and I will set it. Entity 4 has radius as well, and I will set it. Okay? Quite simple. Then I have as well another system called compute rectangle area system, where here I just say, give me all entities which have width component and height component. Those are two data points which I need to compute the area, right? I get the entities which has this, and then I can compute the area, and then I have all the areas set in a way, right? Now the last step in this problem, I would like to compute the sum. Now here's the thing, with here the compute sum of areas system, it's actually only interested in the area component. It tells you, give me all the entities which have area component, and I will just sum them up, right? And then do something with it. Because we didn't define yet what we would like to do. In this sum system, I could show it on screen, I could send it over wire, or I could store it in another component. Now let's unpack a little bit about the systems. Systems, what they do, they are quite different. So they feel like functions, right? They just say like, give me following things, and I will compute something. But with systems, they query for data. They don't get, or dependent on implementations, there are different implementations of ECS. Sometimes we just say like, there is this world end component, which is injected in the system, and then the system can just query for all the entities which have radius, for example. Or sometimes it is possible to, as a system, you define, I'm interested in radiuses. And then something outside will just inject this data into the system, and when it's executed, it will just run through the injected set, which it has. Depends on the implementation of ECS library that you have. Okay, systems don't return. They compare to functional programming. In functional programming, you have input, output. Always. You have some side effect functions, but specifically in Haskell, they just try to like go around them, have like IO, monad, whatever. To just, we don't try to not think about side effects, right? Here it's actually like directly the system does a side effect. It either changes state or performs a side effect. It doesn't return anything. It just does the things that it has to do. Okay, so for example, here we say we introduce another component, which is called sum of areas, and then the system will just set this value for it. Also, what in some implementations we can do, we can define this component as unique. What does it mean? It means that there should be only one entity with this component. It doesn't make sense to have multiple entities which have sum of areas in this particular scenario, right? It could be a different scenario where we say like, okay, we would like to have multiple and so on and so forth. In this case, I decided I would like to define it unique. So basically here we have a new entity which is created to represent the sum. Okay. Systems don't care about the whole picture because they query. They say, please give me only the entities which have radius. I don't care what it has otherwise. I don't care about the higher concept of circle. I just care about, in my domain, I would like to get a radius and I would be able to compute an area out of it. So basically what we can have a much bigger table in a way with lots of different components. And then for certain systems, we are only interested in certain types, properties in a way. And as well, it would be easy to just like say entity 2 is now have width and height, so it's a rectangle. I could just remove these components, add a radius to it, and now it's a circle. So a shape shifting in a way is very easy with such a flexible way, which is really important as well in games, because like the run of like you can have a person, you can have a wolf, you would like to have a werewolf. To modulate something like this in object-oriented programming is quite hard because you probably would like to have multiple inheritance and it has its problems and so on and so forth. Here we just say we have components which represent a person, we have a person which represents a wolf. If we have all of these components on this entity, then it's a werewolf in a way. Okay? And also, some systems don't care if you are a werewolf or a person because they will work only with the data which is important. So if, for example, I say I'm a person if I have a name, then, and you have a greeting system, it will greet you if you are a person or a werewolf. It doesn't like care about it. So it's very inclusive in a way, right? So. Okay. This reminds me of this story. Who knows the story? The Elephant and the Blind Man. Only a few people. Yeah. So it's an old parable comes from India actually, and the idea is following. It has two endings, but the idea is following. There is a king who invites lots of blind men and put them in front of an elephant. An elephant is big, right? And then he asked them to touch the elephant. And dependent on where they are standing, they are touching the elephant in different places. And then he asked them to describe what is an elephant. And there are kind of two endings. In one ending, they start to fight with each other because, like, dependent on where they touched the animal, they have a completely different idea what an elephant is. In the other ending, they try to help each other and like kind of describe it and actually try to realize what is an elephant. If I project this metaphor into ECS, I would say the systems are the blind man. They only care about one part. Your application state is the elephant. Very big thing, very complex, lots of things inside. Right? But the system is just interested in one small thing, radius. It just works on the radius. It doesn't care about all the other parts of the elephant. It can query for one part in order to do its job, do it well, and then it's done. Okay. Interactive versus pure computation. So what's the difference in a way, right? So you could say that we can divide things that we do into interactive computations and pure computations. Pure computations is input in, output out. And we have some kind of a transformation of data. Very typical what we do with functional programming. For example, a compiler is a pure computation. You have files. It will run through a compiler, do very complex things inside, but at the end, it will spit out executable, and we're good. Right? Then, for example, stateless web service. Request in, response out. Something very complex in between, yeah, but generally you could say like it's a pure process, pure transformation. With interactive computations, we talk about applications and games where things run over time. They run in the loop. So basically, it defines that the input that I have now is based on the output from the previous loop and user interaction. Because, like, for example, we could say, like, a browser, you could say it's a pure, if it would be a web browser, if it would be a pure computation thing, you would say HTML, CSS, JavaScript in, pixels out. Right? Works if you would like to print out the web page. But you can scroll it. Right? If you would like to scroll it, you would actually have to have the state before. Where were I before? There was an input of scrolling, and now I will change it accordingly to the previous state. This works for simulations, for games, and applications the same way. So this is interactive. We have this, the computation is done in a run loop. It waits for the input. Okay? So what about this system thing? So like basically ECS, in ECS, systems are executed periodically. Right? And as we designed the systems, we said, okay, give me all the radius, and I will compute the area. Right? And then we say we would like to execute it every frame, so 60 times per second. Meaning that we will be recomputing the area 60 times per second, which you can actually do. Like, interestingly, if you speak with game engine developers, they actually say, like, so what? Because generally, if you have certain throughput and you have certain amount of things which change all the times, and in the games, as they are very interactive and things are changing all the times, it's sometimes more performant just to recompute things all over again than just to try to figure out, sometimes I would like to compute, sometimes I would like to skip. It is different for UI applications. If you think, for example, imagine Microsoft Word, like empty sheet, just think about it, empty page, and you think about it like how complex this one is, and then think about Pac-Man. Is there Pac-Man on the machine there? Yeah. So you can actually try it and play it. Like, think about how much stuff is happening in Microsoft Word when you look at it, and on the Pac-Man. Actually, there are much more things going on in Pac-Man, in very old game, than in Microsoft Word, where stuff is static. Because the UI application, normally, they are more stale. They are waiting for the interaction. Until you don't do anything, it's basically frozen. When you start interacting with it, then lots of computation will be spawned. But in the game, actually, lots of computation are done on every frame. So sometimes it's okay to say, like, I will just recompute this stuff over and over and over again because the throughput that I have from the data throughput is anyway quite high. But if we have something which is normally stale, and the refresh rate is not that high from computation, then you could think about, like, I wouldn't like to compute this over and over again because it's really not necessary. What do we do in this situation with in ECS? in entity component system where we say we execute systems periodically on every frame. In this case, we have, so how to implement an early exit? Early exit means like we will still execute the systems, but they should just say like, I don't have anything to do. I will not go through hundreds of entities and just compute the area again and again and again. Because the previous computation is good enough for me. So there are two options. First of all, we could define better query. We could say, okay, get all entities which have radius component and don't have area component. Right? In case that we have area component, it won't be in the set anymore. Therefore, the set will be empty. This is an early exit for us. Otherwise, if there is no area, everything is good. Okay? However, we spoke about it's an interactive simulation, right? It's not only just, so things can change. Like what happens when value change out through an user interaction, or for example, I could say that this data is actually coming from internet, from network. And I get like updates of these radiuses from time to time. And they change. What do we do then? In this case, we have basically two solutions. We can say like, okay, we would like to introduce a special component for outside interaction. Like if you have done any UI development, you also know that like nowadays it's all hidden in a way, but like specifically if you are kind of old school, you know for UI there is also a dirty flag. Telling you like, okay, this is UI, it's like it's cached how it is represented, but we would set a dirty flag, meaning that we would like to recompute. You could do the same with ECS. You could introduce a special component saying like, okay, something changed. So please do the, and then you would say like the query would be if I have a radius and a dirty flag. Then I compute the area for it, okay? Second solution is you could use an ECS which supports reactive systems. Again, depends on the implementation. Not all of the implementation of ECS libraries are actually supporting reactive system, but some do. So what is a reactive system? The idea behind the reactive system is following. I say that in the query, I say, don't give me just all the entities which have radius. I say, give me all the entities which got radius added or changed. So it actually, it's not just querying, but querying defined on an event which happened to this component. If it's a new component or the value of a component have changed. Then and only then I will execute the system. So if there was nothing and I added radius, now I have to compute the area, right? And if I change the radius, then as well I have to compute the area. Okay, so component events can be added, removed, replaced. I just spoke about it in a second. And then if we think about it, if we would like to change our computation to reactive systems, we can actually say like, okay, the sum of rectangle, we already said, it's dependent on radius which got added and changed. The computation of the area for rectangles is if one of those got changed, right? Then we get like the list of entities which have this things changed. And then for the sum of areas, we say we are only interested when an area changed, was created or changed. However, in this case, is actually, here, in these cases, it's okay, we get these entities, and we just say, like, we will just compute these things on the entities. If on entity 1, the radius have changed, we recomputed the area, then in the sum system, we will just get this one entity. But we would like to include all of them. right? So we will still would like to say, okay, give me all the entities which have areas. The set which says collect things which just changed becomes just a trigger for your system to start. Make sense? Kind of? So basically here you just work with the data which changed. Here you would have to still get everything, but you only execute it when something have changed. So it becomes a trigger. It doesn't become your direct input in a way. Okay, so comparison ECS with functional programming. So basically, again, ECS is built for interactive computation, where functional programming is, in my opinion, more suited for pure computations, where you just have input-output, and you have this function composition, in a way. With ECS, it's actually built for querying data and interacting and looping through it, right? Mutation is okay. Side effects are okay, which are actually dirty words in pure functional programming. Here you say just it's a fact of life because we know we have lots of changes going on. If we would say we would like to have it, like you could write an ECS which just always changes. The problem is when, imagine you have like a game with 60 frames per second, so you change stuff 60 times per second. If it's in VR, it's 90 times per second or 120 times per second. 5 minutes, you're out of memory, basically. If you don't have, like, either you have really good garbage collection, where you just try to figure out, okay, this data is not used anymore, so I can throw it out, or you just say, like, mutation, I have to do this because the situation is as it is. Okay, ECS versus object-oriented programming. I think the main difference is basically that with object-oriented programming, we think in terms of abstractions, right? We thought about we have a shape, we have a circle, we have a rectangle, and then they do stuff. So we basically go top-down. Most of the time in object-oriented programming, we think about like we have this situation where we have a person, we have an account, blah, 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 right? With ECS, we are data-driven. We go bottom-up. We just see like, okay, what is actually the data we have? Because, for example, like person, what is a person? A very philosophical question, depending on the context, right? So like, if I'm in the context of a game, a person could be just a 3D model. If I'm in the context of an address book, it's the name and the address. Both classes will be called person. They are completely different, right? Here, in data-driven, we basically say like, okay, we have a name, we can greet someone, we can combine it into the, like we have last name, first name, we combine it into a bigger name and so on and so forth. And it's all about the data, what we actually have. It's not about the abstract thing, in a way. So what about clean architecture? So we spoke about this, if we do OOP, we do this solid principles, and how do they apply in regards to ECS. So solid, first one is single responsibility principle. Actually, like, responsibility is a very tough concept because everyone thinks differently what falls into responsibility of something. For example, in the ECS, from an ECS point of view, we separate state from behavior. We say that storing data is one responsibility, mutating data is another responsibility. Object-oriented programming, say class, actually stores and mutates it. In this case, it already falls through, but then again, I could say like responsibility of the person class is to do stuff which relates to person. Responsibility of this app is to do things. So basically, I can have one class which implements the complete application and saying, this is the responsibility of this thing, so it works. So it's kind of a little bit shaky, but I think because of we going from data and bottom up, from my experience, the Disassembling of responsibilities is actually much nicer in ECS because we will see definitely a system which does have too many responsibilities. It will depend on multiple components. Actually, normally you see if something have lots of responsibilities, you will have less components and like much fatter systems in a way. If you have more components and small systems, then it's also much more composable in a way. Then open-close principle. To be honest with you, I actually don't like it at all, and I can explain why. So the idea is generally fine. You say it's open for extension, closed for modification, but I saw lots of people actually going a little bit bananas on the concept, saying like it's just closed for modification, you shouldn't modify it, which kind of forgets that we are human. We make bugs. If it's closed for modification, it's closed for modification. If there is a bug there, I shouldn't be able to actually, I should be able just to extend it, right? Sometimes it's not even a bug. Sometimes it was, the specification was wrong, or it was different. I have to change it. Almost closed, almost open. And then the question is, and like the problem is you need open-close principle if you build stuff on top of each other, right? So basically you say you have this base class and then you have another class and another class and another class. Because if it's open for modification, then the whole tower can fall apart in a way, right? With ECS, we say the systems are kind of horizontal. They're just like small systems which are executed one after another. They don't directly depend on each other. They don't communicate with each other. They communicate through state. They just change state. So for example, we have the sum system, which just, if we will have areas on entities, it will compute the sum. But it doesn't know anything about the area computation systems, and it doesn't need to. Right? So it's much more loosely coupled in a way. Then, Liskov substitution principle. This one is also very important when you have inheritance. You say that if you have a type and you substitute it with a subtype, then it should work kind of the same. But in ECS, we don't have inheritance, so we don't have any problem. All right? So, like, just so interface segregation principle. Here, basically, the idea is that you have interfaces, and it's important if you have classes which talk to each other. And this is as well something which we saw in this small example of sum. The sum is talking to abstract shape, asking it for area. And then with Liskov segregation principle, the idea is to have many small interfaces, basically, and not one big one, because composition is a good thing. It's kind of similar with ECS, but in ECS, actually, systems don't talk to each other. They don't have API to each other. The only thing is components. So we try to segregate components. We try to make the components as small as possible so that they compose well, and that we can like also distribute the computation to multiple systems in a way. Okay. So dependency inversion principle in ECS, basically we even inject data, not even dependencies. System just like it doesn't own the things anyways, because like basically the idea of dependency inversion principle is that a class shouldn't own its dependency. It should be open for injecting the dependency into it. Systems are actually even open for data. They don't store the data. They just ask for data either from context or in different implementation, it gets directly injected into the system before it's got executed. Okay, let's talk about testability. With object-oriented programming, if you follow solid principles, then stuff is kind of testable, right? dependency injection is very important so that your classes are accessible, so that you can like define the precondition in a way that you can execute a method and then just check if post-condition is how you expect it. With ECS, it's actually even easier. You have a system, you say, okay, I will initialize the context in a way, or the world in a way that I expected. I will execute the system and then look at the context and see if it's in the state that I expected. Also, when we speak about unit testing, what is a unit? In object-oriented programming, it's kind of like class, method, class, maybe a couple of classes, and so on and so forth. With ECS, you can just say like unit is a system. It has an execute, you prepare stuff, and then you just execute it, and this is your unit test, in a way. If you have integration test is, however, if you have these systems which are defined in an execution order. So in the integration test, you prepare your context, your state, then you execute these systems in order, and then you check it. This is an integration test where you executed multiple systems. And you could also execute them in the loop. Like, for example, if you would like to say, I actually would like to resimulate 2 minutes of gameplay or application runtime, whatever. You just would say like, okay, 2 minutes equals 220 execute calls of those systems. And I will just execute them like this, and I will check at the end if I get the stuff that I expect I should get. Okay, debuggability. This one is a little bit harder because in the typical ways how we debug, we just set a breakpoint somewhere, and then we just hop along, right? So in the object-oriented programming, it will be like one class will call another class, one object will call another object, and then you can just hop along, and you basically at some point you will get to hopefully to the place where you want to get, specifically if the code is not multi-threaded. If it's multi-threaded, then it becomes a little bit more of a pain. If it's single-threaded, then you can just hop along. With ECS, basically, it's easy to put a breakpoint in a system, but then it's harder to say, like I would like to have like the sequence of systems. In this case, it's much easier to create an integration test. If you have a situation which you would like to debug, just create an integration test where you have the systems which are called multiple time in the right sequence as you expected, and then you can debug and see what's actually happening. If it's a bug which is kind of depends on the like systems playing together nicely in a way, if it makes sense. However, what is actually good with ECS is that you can have runtime debug tools. Because all the data, we separated it. Systems are basically stateless. If you would like to see what kind of state you are in the current situation, you just need to see the context. You just need to see the spreadsheet. And then you see basically everything. And you can, different implementations have different toolings for all this kind of stuff where you can, at runtime, actually see what actually happened. You can also record all the changes, how it led to this state. Because all the state is actually will be represented. Therefore, for example, if you're familiar with aspect-oriented programming, who's familiar with aspect-oriented programming? Just a few people. So like the idea is basically that you have something which you would like to execute. Like, for example, you have logging as a typical example for aspect-oriented programming. You say, I have following methods which get called with following parameters, and I would like to inject something in there so that I can log the input and the output. It's done either with some dependency injection magic or bytecode manipulation magic and so on and so forth. It depends on what kind of language you use. With ECS, it's basically if everything is reflected in components anyways, You can do logging with systems, which say, like, for example, I would like to log when the area got computed. I would like to log each time when we compute a new area. This system is just a reactive system which monitors the area and will just print you out the area. Another system will log you when the radius have changed. So when you do this separation of state from behavior, some tricky concepts become actually quite trivial because everything is kind of exposed and we don't have this encapsulation and data hiding, which we tend to do in object-oriented programming. Okay. Performance. This is the last point, by the way. I know it's late, so performance. So, like, generally there are two like type of people, how people come to ECS, at least in the game development. So first, and I kind of include myself to this camp, is basically people who wanted to have like a very flexible way of representing game state and being able to change stuff very easily because, as I talked about, everything is very composable, everything is very like, tightly defined. There is another camp, though, who comes to ECS purely for efficiency. Because the interesting part is basically when you design your code in a way where you have system which does only one thing and iterates on data, then you can design your data and systems in a way where it becomes very efficient to do stuff. How so? Here is a table from this website. There is actually a blog post behind it, which explains like the CPU operations and how expensive are they. Right? So we say here it states if we have a simple operation like add or something, it's smaller than 1. Who knows why it's smaller than 1? It's less than 1 operation to make an addition. Generally, it doesn't make sense, but the idea is kind of current CPUs have so-called pipelining and SIMD instructions. SIMD means single instruction, multiple data. Meaning that if you have, like, for example, you would like to add multiple things together, they don't correlate to each other. So, for example, you have a vector, and you would like to have an addition. If the numbers are small, remember the representation of numbers is, can be different from the previous. Then you can actually pack in the whole vector inside of one instruction. So you would like to have 3 additions, and if you are lucky and your numbers are small enough, you can actually do it in 1 operation. Meaning that single addition is actually smaller than 1. You just did 3 additions in 1 operation, in a way, or 2 additions in 1 operation, right? But it could be, so then we have a memory right. This is like around 1. Then we switch from float to ints. It's from 0 to 3. I guess 0 is for the number 0 because then you don't have to switch. If you do have to switch, then you have to recompute, as we saw in the previous talk as well. Then we have this so-called branch predictions. We are in the we have an if statement, and it's how the CPU hoped that the computation will go. Anyway, we have floating point addition. This is the interesting part. Who knows what L1 is? It's a cache, right? So basically, what we have is in the CPU, in our computers, we have RAM, where we have the data, but the RAM itself is quite slow because it would be expensive to build it in a fast way. For the fast hardware, we only have so-called caches, which are directly on the CPU. And we have multiple of them. We have L1, L2, L3. Depends on the CPU. Different CPUs have different level of caches. And the L1 is like, I don't remember how big they are, but basically the bigger the number, the bigger the cache, right? So the idea is we need to put the data from RAM into cache. And if we would like to add things, first we need to load it into memory. If we have a typical object-oriented approach, is we have an object which is somewhere, and then every property, it's a reference to something else. So it's basically all across the heap, all across the memory. How the CPUs, what they do when they load stuff, if we say like, please read something from here, they already read into a page, so that they already put stuff, can cache things, because they hope that the next data that you need will be close by. With ECS, when we design how we store data with ECS, we can actually design the ECS library in a way which will store the important things close by, so that we won't have so-called cache misses. So the things are stored sequentially. For example, radiuses, all the radiuses are stored close by. You have hundreds of radiuses, they are all stored in one contiguous array. And then you won't have any like jumping around and finding the next radius. Because, for example, if you see loading from L1 is 4 and loading from RAM is 100, which is 25x. So if you have cache misses, you could produce a 25x of delay. Interestingly, normally when we speak about efficiency, we speak about O notation. Who knows O notation? Like algorithmic notation. We say like it's n, it's quadratic, it's log n, and so on and so forth. Interestingly, sometimes we say something is, for example, n, and it will be much faster than log n because the logarithmic notation doesn't care about time we spend loading stuff. So for example, we have a linked list. We say appending, like searching through it is actually, or better yet, we have a tree. And it could be that the data is actually everywhere because there is no need to keep it together. So we say actually accessing, finding something in the tree will be log n, something in the array will be n. But if the data here is completely fragmented and we need 100 cycles for every lookup, and here we need only 4, it then really depends on the n. If the n is still huge, then at some point log n will win. But if the n is not that huge, and you can aromatize the 25x of lookup, which we pay as penalty, then this smart data structure will be actually slower than the dumb data structure, in a way. Okay, so like if you want to know more, actually you can have a look at the work that Unity 3D, this is a game engine, people doing there. Actually, they say the way how you program now with Unity 3D is pretty much object-oriented. And they say that they see 100x speed up if they lay out stuff in ECS way. So now they are doing lots of research in this direction to actually switch. You will still be able to do the things in object-oriented way as well, because not every game needs to be efficient or have big problems so that you need to like process 10,000, 100,000 of things directly. But like they now also investigating into writing the games in the ECS way, so that it's, for them it's purely for performance. They actually come to this pattern purely from performance perspective. If you're also interested in the performance, there is a great Mike Acton talk from CPP-Con 2014. Who saw it by any chance? Nobody. I can highly recommend. He speaks about this cache locality stuff and data-oriented stuff, and also like the mismatch that we have in object-oriented programming, where we think that a person is a person or a table is a table, where actually no, it depends on the context. And table can be different things in different situations. Then there is a nice talk from Catherine West from RustConf 2018, where she actually explains more the modularity approach of ECS. And she has a very nice example how a larger game can look like if it's implemented in object-oriented programming style. She has like, I don't want to spoil it, but you will see it in the, in the video if you're interested. Okay, and then a shameless plug. I started a meetup in Berlin. It's called ECS Lab, and we have a Discord server. So you are welcome to come in Berlin if you are like happy to travel. But we also have like a Discord server. It's basically something like Slack, where we talk about ECS and so on and so forth. So this is probably more approachable to kind of get some information out. And we also will try to post presentations and videos and so on and so forth in this, on this Discord server. Okay, then thank you very much.
Thank you. Okay. Any questions? It's not the same one. Thank you for the presentation. It was a very cool new way to think about things. I was wondering, do you also have references in these component systems where you can, in one of the components, you can refer to other entities?
Yeah, so I actually wrote a blog post just about it, and it's again depends really on a little bit on the ECS implementation, right? So like the point is, we like to think about references more the same way as relational databases think about it. So you have some kind of an ID and you store it as a component. It can be a list of these IDs if you have like one-to-many, right? If you have one-to-one, it's just one value in a way. And you can also, like, depends on the implementation, sometimes you can also like store the entity itself. The entity itself is normally, it's either a class which holds components, or it's just a number, just an ID. Right? So if it's just an ID, it's kind of safe to have it, to say like, I'm just storing this ID of this entity and this is my friend, for example. Like I would like to represent friends relationship, for example, right? The problem is, again, if you store the entity ID, if you would like to then serialize this stuff, the ID is not stable. So it's better to have your own ID actually, and then say like my friend has this ID, and then I can just look up. There are also possibilities to have lookup tables in ECS where you just say not only give me everything which has an ID, you could say just give me everything which has an ID and I will filter through it. Sometimes you have a possibility to say give me something which has following ID. So querying by value, not only by the property that it has, but also by saying like this is equal. And it's in a way the whole idea is kind of very similar to relational databases, but in memory and very efficient. Right, so it's basically just you building up a table of things, and if you would like to refer to it, you refer it by some kind of a foreign key in a way.
Thank you.
Right? Okay. Any more questions?
Yeah. Ik wou het eerst even vragen. Well, thank you for this presentation. It seems like A very interesting programming paradigm, actually. I didn't know that paradigm, but it seems very similar to reactive programming in a way. So my first question is actually, could you point out the precise difference between these two paradigms?
Yep.
Second question is, what kind of a type system is typically used in ECS?
Okay, so for the first one, comparison to functional reactive programming. The difference is basically in a way that you also, like in functional reactive programming, you say you have something observable and different things can subscribe to it. And then if it changes, it depends a little bit on the scheduler, right? Normally it directly fires and tells you, so it's a synchronous call. Or there are sometimes also schedulers which are asynchronous, so they are kind of accumulating stuff, right? In ECS, basically, and another thing, with functional reactive programming, you have multiple streams in a way, right? Every observer, like, again, depends a little bit on the scheduler. You can have different schedulers which try to aggregate things. But normally, it's kind of like every observable becomes its own stream, its own emitter of events, right? In ECS, actually, there is only one stream, it's time. It's how often we execute things. And the events, they are materialized as data. Also, in functional reactive programming, normally you have kind of, this is event, and this is either captured in the function somehow, and then through a call, it will be propagated and so on and so forth. Here, actually, the events themselves, they are part of, everything is data. Events are also data. References between things are data, in a way. So basically, for example, from debuggability perspective, I can pause and just look at the context and see all the events which are currently in there. I could also say an event, I have an event and I have a timestamp component. So when I emit an event, I emit the event itself, and then I also add a timestamp component so that I actually know when this event was fired. So because we have this entity which has this event component and timestamp component, which is, again, actually orthogonal to each other. So you don't care, as a system which needs to just react to an event, it doesn't care about the timestamp component, but for you as the person who debugs this, it's actually a very interesting information, right? Then talking about the type system. So basically it depends on the host language, right? So it's kind of like, there was actually one language which was kind of completely language for its own for a similar paradigm. It was called with Eve, maybe you heard about it. It actually didn't directly told that it was an ECS implementation, but if you think how they approach things, it's actually ECS. It's everything was query-based, so you can write small snippets which say, like, I'm interested in this and this and this, and then I can change this stuff and so on and so forth. So if you don't have, and probably you don't have a language which is like actually ECS language, right? Then you have a host language like C#, Java, JavaScript, whatever. And then the type system is actually based on this one. So the component is a type. An entity is, if you want to, I always call them, it's a polymorphic object. Because basically you can say, I will give you an entity, and you will just pattern match on this entity which kind of components it have. If you query, if you say, give me please all entities which has this and this and this, then it's safe for me just directly to unpack this because I know it's always up to date. Even though I have an entity type, I know I can just directly access these components because what I actually asked for is an entity which has radius. So I know radius is there. So it's still typed. It's not like it's not just like a dictionary where you get an any type and you can just suggest something. It's the simplest implementation of an entity is actually, it is wrapper around the dictionary, but the key is then the type itself, so the class, right? And the value is then an object which implements a component interface. And when you, if you have generics in your language when you can just say get, and then in generics you get the type, and internally the entity will just look up if this dictionary has the type you need, and internally will cast it. But for you, you as a developer, you get a completely typed API through generics, basically. Again, like for example, the implementation of Unity, currently they have two options. You can either query, or you can have this injection. With injection, they basically say like a system have a property with an array of a certain struct, which has like one property of a type, another property of a type, and they will internally, through reflection in the beginning of when everything is set up, they will know how to inject this array into your system so that you work on an array of, for example, radiuses, or the system works on an array of width and height, tuple, or just a local struct which has those two properties in a way. So the type get preserved. We just don't need this abstract type. We don't have to tell it's a circle, it's an entity. And it depends on what is inside, so it's very democratic in a way, right? So like, it's really not how I was born. Like with object-oriented programming, it's defined with how the object was born, right? It was born as the following class, and then it is this class. With ECS, it's basically every entity is born equally. In a way, it's empty, and then depends on what you insert into it, then it becomes something. As I said, person, wolf, werewolf, whatever. Circle, rectangle, and so on and so forth.
Actually, I want to go to the last question for a moment. So,
There is one.
So near the end, you talked about performance,
Yeah.
and you explained that since systems only care about a few components, and components for all entities are stored linearly, the performance is great because we don't have cache misses.
Yeah.
So that made me think, was ECS designed around this property first, and then the rest spawned out of it, or is it a lucky byproduct, and the ECS design was made for its simplicity?
It's real. To be honest, it's really hard to tell, and it depends on. Like the first appearance of the pattern was I think in '97.
I saw Wikipedia, it was in Thief, the game.
Yes, with Thief. So like again, the problem is in the same Wikipedia article, it tells that Unity is based on ECS, which is actually wrong because they just start doing ECS now. Previous, like this game object and mono behavior, which they have, is actually not ECS. There is a game object entity, there is a component, there are no systems. The components themselves in this paradigm, so you have like this entity component, and then the component itself is more object-oriented. It stores data and also has an update method, which manipulates this data. So, and why I'm talking about this is basically what was in the Thief is also really hard to tell. Like I found the presentation and I looked through it. It seems like they're actually separating state from behavior. But for them, it was more important that they have like this data-oriented approach, so they could just represent things as data, and then game designers could easily compose things, and then it just works for them. So this was, I think, their initial thing. But for example, if the whole thing we're talking about here is in the called data-oriented design. Data-oriented design is actually more towards performance and kind of making software data-oriented and also easier digestible for the machines in a way. Which, from my opinion as well, from architectural point of view, at least from ECS point of view, it's also quite digestible for people as well if you kind of have this separation from state and behavior. So yeah, hard to tell.
thank you. If there's any other questions, we can do it, I suppose, after the
Okay.
so we're after rounding off. I want to thank you one more time. One more applause, please.